Right, in the handout that you've got there, or you haven't got yet, which I will email to you, in the handout for the second half of the History of Astronomy bit, we've got a very famous diagram there. Okay. As I said, I like to think of the section on the History of Astronomy in two bits. You've got ancient astronomy, and the finishing point for that, if you like, is the idea of having the sun, we'll start again, having the Earth in the middle, slightly off centre. Do you remember that from last week? You put the Earth slightly off centre, the planets and the sun and the moon all go around it, but to make things more accurate, to get more accurate predictions, you also include, which is the idea of epicycles. Do you remember that? So each planet goes round, may not be one actually, in fact planets like Mars had several, but basically the planets go round little mini-circles, I beg your pardon, called epicycles, and the centre of their epicycle goes round the Earth, but things work better, I'm making a mess of that, things work better if you put the Earth slightly off centre, okay? Using that kind of system, people, like the people who built the Antikythera mechanism and stuff, were able to make pretty accurate predictions of where the sun, the moon, and the planets were going to be in the future. Okay? But it took a very long time, it was very hard work, and sometimes the calculations would take as long as the actual things they were trying to predict. After that, there's quite a big gap. Okay? Here we've got things like Ptolemy, 2nd century AD maybe. How much progress is there, really, until something like the 1400s? The answer is not a lot. So you've got a big chunk of stuff here where not a lot happened. Okay. Now astronomy continued, people continued to make observations and so on, but in terms of a theoretical model, a scientific model that can predict what's going on, there wasn't really a lot of progress. Okay. Until we come to, very famously, the work of a gentleman called Nicholas Copernicus. Okay. And he's the next big name that you need to know about. But be aware, between somebody like Ptolemy and those guys and Copernicus, there's nearly 1,000 years gap. All right. How much further could they get? Well, I'm sure if I went to somebody in Skipton High Street and said to them, what's wrong with this model? Many people would point out the big mistake is it's got the Earth at centre. Okay. That's true, but actually that has relatively little effect on your predictions. If you think we're standing still and everything else is moving, well, you're wrong, but what effect does it have on your answers? Very little, okay? Because we're all out in space, deciding who's moving relative to whom is a bit of a waste of time, okay? There is another problem. There is another problem with this model which is far less easy to see, okay? And Copernicus really started the ball rolling in terms of understanding what was wrong with this model. Okay. Now, famously, if you look in your pack, which is on the screen, you can see there's Copernicus's famous drawing. I've seen it on coins, actually. It's such a famous thing. Very, very famous drawing. I'm sure your medieval Latin isn't brilliant, but you can probably have a go at what's in the middle. Is the sun. All right. Copernicus said, why don't we put the sun at the centre? Okay. Now, there's two things we need to be clear about with Copernicus. His reason for doing that, okay? Copernicus was employed by the church, and he really wasn't about going around saying, I think the sun's at the centre, okay? There's a bit of an issue here because the Bible, which doesn't actually make particularly clear on any particular point, but if you read the Bible, generally there's no suggestion the sun's at the centre, all right? As you might imagine, people talk about things with the Earth at the centre, okay? So saying the sun is at the centre, as you probably know from later people like Galileo, caused a bit of friction with the Catholic Church, certainly. Copernicus said, if you put the sun at the centre, okay, then, and have the Earth going round, all right, and have your planet going round as well, like that. Now you look at that and think, well, gosh, that's much better, because that's what's actually happening, that's true, okay? And indeed it is. How much will that improve the quality of your predictions? Not very much, really. Have yourself at the centre or have the sun at the centre. It doesn't make a lot of difference. It does make the calculations easier, though. It's much easier to explain, as some of you know, the backward motion of the planets. When you think about the fact, well, the Earth is moving around the sun, and the planets are moving around the sun, something like Mars, for example, is moving around the sun more slowly. So as we go round the sun together, the Earth kind of undertakes, it sort of overtakes Mars on the inside, And if you can imagine being like cars on a motorway or something, if you can imagine being on the Earth, as we undertake Mars, what will Mars appear to do? You ever done that when you ever take a car on the motorway? Yeah. If you forget about the road and the trees and stuff around you, if you just focused on the car's going backwards. As far as you're concerned, from your moving point on the Earth. So getting the Earth moving around the Sun makes the calculation much, much easier. And generally in science, that probably means you're on the right track. If the maths is very, very difficult and very complicated, it doesn't mean that you're wrong, but if you can make the maths easier, that's probably a suggestion you're on the right track. But Copernicus was very clear. He proposed this mathematical model because it made prediction much easier. We explained last time that a lot of these people, Copernicus included, made their living out of predicting horoscopes, out of astrology, out of people saying, I'm going to invade the country next door next week. What's the position of Mars, the god of war, which constellation is that in, is it good or bad? And he was doing that all the time, and he must have got sick to death of doing like 4 epicycles and all sorts of stuff like that. And he proposed this model. He found that if you put the sun at the centre and have the Earth moving, predicting what direction you need to look to see the planet against the background of the stars becomes much easier. Okay? He did not get more accurate predictions. A lot of people think as soon as Copernicus put the Earth at the centre, everything became really easy. Well, that's not true, and it's important that you understand that to see how a couple of other things fit in afterwards. All right? So this model is just better, it's just faster, it's easier. You can make the calculations in hours that would have taken you days using the ancient model. Okay? Copernicus didn't publicise it a great deal. As I say, he was employed by the church, he was a priest. He could probably see that it wasn't going to go down well if he started publishing books saying, actually, the Earth isn't at the centre. As I say, the Bible isn't specific about this, but there is a point in the Bible, it's the battle of something, where somebody says, for some reason, they command the sun to stand still in the sky. There's a bit in the Bible somewhere where somebody says, they command the sun to stand still in the sky. All right? And the argument is, that they wouldn't have said that if this were true. All right? So Copernicus kept this book quite quiet. I mean, the diagrams you see there, he did have it put into a book. Copernicus apparently, I mean, a lot of his colleagues said, this is really good, you've got to tell people about this. He was pretty cagey about it. He didn't want it being publicised. There's the famous story of the first printed copy of his book being rushed across Europe on horseback to be put in the hands of the dying Copernicus. I'm not sure how true that is. He certainly came up with a system which scientists and astronomers liked a lot because it reduced the time it took you to make calculations. It still included epicycles. I'm still trying to find a diagram of this. The one on the board there, I mean, if you Google for Copernicus' system, it's all this stuff about everything going around the sun and, fantastic. Copernicus had to use epicycles. I can't really find a diagram that shows you this, but it's a true fact. The Copernican model, yes, it has the Earth, the sun at the centre, and it's much better, etc., 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 but you still have to have epicycles. This diagram doesn't show that, and most of them don't. He still needs to have epicycles. All right? These are important points which are not stressed in many books, but they're very important in terms of the next few discoveries, which don't seem to make sense unless you understand these things. This is not more accurate, it's just quicker. And it still contains epicycles. No, that's a good point, actually. Have we learnt these words from last time?
Yeah.
Heliocentric. These are words you need to know for the exam. Geocentric, fairly obvious meaning. The heliocentric view goes way, way back. All right. The heliocentric view, the ancient Egyptians have, suggested. To them, the sun was quite important. I can't remember if it was the sun god. Was it Ra?
Yeah.
But anyway, their chief thing was the sun. The idea of a universe centred around the sun would not have been a problem, I think, to the ancient Egyptians. Okay? So it's not a new idea. Again, Copernicus suddenly thought, let's put the sun at the centre. I don't think so. People had suggested it, but before then, this was Copernicus' real contribution, he showed mathematically how much quicker it could make things. No one had done that before. So it's important. Copernicus is often like the great saviour of astronomy. Absolutely, his discovery is totally pivotal to the whole thing. But you need to be clear what it is he discovered. He realised that the heliocentric view, which has been around since ancient times, okay, the heliocentric view could be made to do these predictions, these calculations of the position of the sun, the moon, the planets. It could do that much more easily than the older geocentric view. Okay? There is I remember reading somewhere Copernicus, when he was training, because he was Polish. He lived in what's now Poland. When he was training, he went to Italy, and just across the Mediterranean from Italy, you've got, it's suggested, some people have suggested that Copernicus, when he was in Italy, would have seen things like pictures of, hieroglyphs in ancient Egypt and stuff like that. And it's possible that he would have got the idea. Where did Copernicus get the idea from? Maybe we go back to the ancient Egyptians, as I say. He certainly studied in Italy and may have seen pictures of or drawings of the ancient Egyptian carvings and stuff. We need to link up Copernicus's discoveries with those of another great mathematician, a guy called Johannes Kepler. Okay? So if we're thinking, what do I need to learn for the exam, then we kind of got, you need to know the people, and you need to know their key suggestion, their key discovery, if you like. You don't need to know they lived in Poland or what year they were born or anything like that. Okay? But in terms of our modern view of the solar system, how do they all fit in? Okay? Copernicus didn't solve all the problems. For example, he still had to have epicycles, which many scientists looked at and thought, this seems very odd. The planets ought to move just beautifully and smoothly, and why should they be going round and round these funny circles? It's just a bit ridiculous. But they still worked. If you put epicycles into this system, you got very good answers, and you got them relatively quickly. That's a really good question. Why do you still need epicycles? Isn't that right? Doesn't Mars go around the sun? And the Earth go around the sun? Isn't that what many people think is? That's totally correct. Yeah? So you don't need anything else, and that's why it's very important to understand. I wish I could find a diagram. The Copernicus system doesn't give the right answers unless you put epicycles in, which is, if you think about it, a big question. Johannes Kepler was on the same thing as Copernicus. He was convinced that the patterns, the behaviours, the curves, the circles and all that sort of things which the planets went in was decided by God, and in his mind he was discovering the hand of God by discovering what was going on. Okay? And Kepler, if you have a look on here, this is Kepler spent many years of his life on this thing called his cosmic mystery. Okay? Now the cosmic mystery, or the Mysterium Cosmographicum, is this ridiculous looking thing. After all this, he went on loads and loads of calculation, and basically after committing 12 years of his life to this problem, he found it doesn't work. Now, this is the turning point in history, and this is why I have tremendous respect for Johannes Kepler. At this point, you would just say, flipping astronomy, I'm off down the pub, and I'll become a rock star or something. To be fair, Kepler got up the next morning and started calculating again. All right? He spent over a decade of his life. He was convinced, a very religious man, he was convinced he would be the first person to see the secret pattern that God had put into the orbits of the planets. When he found these 5 platonic solids and thought they must be linked to the orbit, it just seemed to fit so beautifully. And yet it just doesn't. It doesn't work. And of course, as we know, the discovery of Uranus is going to completely mess the whole thing up. Now, Kepler was a great scientist because he got up the following day and started wondering about why it didn't work. Many people would have just given up. Kepler, having seen that his cosmic mystery thing didn't actually add up, then what he did was to start looking at why it didn't work. And he focused particularly on the planet where it kept going wrong. Kepler looked particularly at the orbit of Mars. All right? Because Mars is the one that always seemed to cause him problems. When he was doing calculations for his cosmic mystery thing, then he generally always had difficulty with Mars. Mars seems to have the maddest orbit in the sky. It does the biggest backward loops and all sorts of things like that. Okay? And he drew a diagram a bit like this one. He basically drew out the circular prediction. This was his prediction with the best data in the world. He predicted his orbit for Mars, okay, around the sun. And he found that it doesn't work. It doesn't give you quite the right positions. But he noticed that it does give you the right positions here, here, and here. It seems to curve inside in those 4, except for those 4 points there. And it doesn't mean the orbit's square, that's just how badly I've drawn it. And eventually, Kepler realised what he discovered. he discovered that the orbits of the planets aren't circles. Something that nobody had even suggested. Copernicus' idea of putting the sun at the centre is actually as old as the hills. No one had really done the maths of it, so, hats off to Copernicus. Kepler came up with the other mistake. We said there was a second mistake with the ancient view. One is they've got the Earth at the centre. That's actually the minor mistake, really. It doesn't have very much effect on the accuracy of your predictions. The really important mistake they made is because their measurement, these differences are very, very small. Without Tycho Brahe's incredibly accurate data, he would never have noticed these things. And to be honest, if you hadn't got someone as painstaking and meticulous and careful as Johannes Kepler, many people would have just missed it. He realised that the orbits of the planets are ovals. All right? They're not circles. Now, the orbits of the planets are fairly close to circles. There are other things in the solar system which orbit with a much more elliptical, there's a good word, a much more elliptical orbit. Anyway, there are things in the solar system that orbit like that. They're called comets. So, for example, Halley's Comet nips around the inner solar system. We all have a good look at it, and then it spends 75.5 years out beyond the orbit of Neptune, and we don't really see it. Okay? All orbits are ellipses. They're ovals. They're not circles. Okay? Where were the clues? Somebody asked earlier very sensibly, why do you need epicycles? If that's right, if Mars and the Earth are both going around the sun, which they are, why would you need epicycles to make the predictions? And the answer is because you've got the shape of the orbit wrong. Copernicus had the shape of the orbit wrong. Notice, and this goes back to those of you who watched the video for the Antikythera machine, notice that you get better predictions if you put the Earth off centre. What's that a bit of a clue towards? It's not a circle. It's a wonky circle, get it? A good way to think about an ellipse is if I put a drawing pin in the table and gave you a loop of string and a pencil, could you draw me a circle? Can you imagine? Drawing pin in the table, loop of string, pull it tight, string would give you a circle. What if you had two drawing pins? You'd get an ellipse, wouldn't you? Can you imagine a circle with two centres? Yeah? Imagine if I got a loop of string and a pencil. There's a diagram like this in the pack. You put a loop of string on that, you just pull it tight, you go round. This is the circle. Don't use the word oval, it's a bit ugly. This is called an ellipse. Okay? It's a circle with two centres. Each centre isn't called the centre of this, it's called a focus. Yeah? As you put the two drawing pins closer and closer together, your ellipse will start to look more and more like a circle. A circle is like a special example of a curve that belongs to the family called ellipses. A circle is the special ellipse where you put the two foci on top of each other, so you just have one point and then you get a circle. Put the two foci, in the Earth, in the case of the Earth, the two foci are very, very close together. And so what you get for the Earth, imagine the drawing pins and the pencil again, you draw a circle that looks pretty circular. If I drew the Earth's orbit to scale, you'd go, blimey, that's a really good circle. Normally you draw rubbish ones. But if you were to measure that distance and that distance, they're not quite the same. I think it's about a few thousand kilometres in 150 million. It's very slightly. The Earth is very slightly egg-shaped orbit. That's why people, up until Kepler, never noticed it. All right? Things like comets have the two foci much further apart. One of them is always the sun. One of the focus points, kind of obviously, is always the sun. Kepler was very bothered about the other one. It's just the mirror image of where the sun is. It's not really significant, but Kepler was very bothered about this other point. But we've just done, gentlemen, Kepler's first law of planetary motion, which there are three, and this is the first one you need to know. Very simple law. The orbits of the planets are ellipses with the sun at one focus. The orbits of the planets are ellipses with the sun at one focus. Okay? Absolutely massive discovery. All right? Copernicus, an amazing step forward, tremendously important, but was still carrying on something nobody'd ever questioned. The orbits of the planets are made by God. So what shape would they be? The most perfect shape, which is a circle. And they're very close. If Kepler looked at comets, if Kepler had studied comets, he might have spotted it earlier, but at his time, comets weren't thought to be anything to do with astronomy. They were thought to be something to do with the weather. And for that reason, he focused all his attention on the planets. And it's down to his carefulness, really, he noticed this very small difference. Kepler's second law says the closer you are, let's take this example, the closer you are into the sun, you have to move quite quickly, and further out, you go much more slowly. Halley's Comet's a good idea. It buzzes around the inner solar system in a few months, and then spends 75.5 years going very slowly around the outer solar system. Now this means, let's just draw an orbit again, okay? It means that there are two important points on the orbit. This point is the point at which the object is closest to the sun, and this has a name which you need to know, and it's called perihelion. All right? Because orbits aren't circles, that means they have a point where they get closest to the thing they're orbiting, perihelion, and they have a point which is furthest from the sun, all right, which is called aphelion. You need to know those words. Okay? In the case of the sun, in the case of the Earth, they're very close together. How far is the sun from the Earth at aphelion? How far is it at perihelion? Not much difference, because the Earth's orbit is an ellipse which looks like this. It's an ellipse where the two drawing pins are very close together, and it looks very, very much like a circle. And it foxed astronomers for thousands of years, up until the time of Kepler. Okay? We can just do this one as well. Let's suppose you're orbiting the Earth, like the Moon, for example. The Moon's orbit isn't as elliptical as that, but it is quite elliptical, actually. If you were orbiting the Earth, I'd like to guess, what would be the point of closest approach? It can't be perihelion, because that's the sun.
Is it something like perigee or something?
That's very good. Good try. Almost there. It's perigee. All right. So the Moon has perigee, where it's closest, and it also has apogee. What's that? You have to put the O in to make it pronounceable. Apogee. Okay. So you need to know perihelion, aphelion, perigee, and apogee. All right. Orbits have to have these now because they're not circles. In a circle, you're always the same distance. That's nearly true for the planets, but not quite. But hopefully you can see what Copernicus did. Many books tell you rather more than they actually did. Kepler, very, very important. Kepler realised that the orbits aren't circles. Something nobody had suggested ever, really, I don't think. Okay? We'll look at Kepler's other laws next time.